Right, okay, so my talk's called Zen and the Art of Tube Amp Maintenance. It's a play on the title of the book, Zen and the Art of Motorcycle Maintenance, which you might have read by Robert Pirsig. The most important thing you need to know about this book is that he introduces the idea of a chautauqua, which is, I might pronounce wrong, sorry if I have, which is sort of like a reading circle or a discussion circle where ideas are introduced and discussed. And throughout the course of the novel, he has these interludes where he's introducing ideas and positing thought experiments around the ideas of quality and value, and kind of trying to provoke kind of a reaction and a, I guess, like, inspiration in the reader. In that sense, this is sort of in the same vein, in that I'd like to provoke some ideas around systems design and component design and software design. Primarily to do with the relationship between four things, right? Informal reasoning, coupling, testing, and feedback, and how those all kind of break down in how we design systems and how we design software. So I have some props, right? I'm gonna ask you a quick question. Like, those two things, without any other knowledge of them, would you kind of feel comfortable debugging those?
No.
Right, okay. If I gave you some tools and explained to you kind of what was going on, would you feel comfortable debugging those?
Maybe.
Right, but that's the thing, you're kind of thinking, there's a lot of information contained in that. Even if I give it all to you up front, even if I document it, it's a lot to take in. Like, getting a mental model of those systems is hard, right? And this is like every system we ever encounter, especially ones when you go into particularly a big company and there's potentially 20, 30 years of legacy stuff that you need to understand, right? So the reality is neither of them you really want to deal with, right? So all production systems are like this. So it's part of, again, what I'm trying to get to is, how can we get more feedback from our systems? How can we reason about them in an informal way? And how can we then translate that into helping us with debugging, helping us with deploying, and all this kind of stuff? So, Brandon, could you pass those around? I want everybody to, just have a think about those. I'm also going to reveal a free thing right up front, that those are actually not even the same circuit. And I don't know if that's obvious, which is another interesting property of those two things. They're obfuscated, right? So yeah, this is Zen and the Art of Tube Amp Maintenance. I'm Alex, you mostly know me. Thanks for listening. So this is a pedal I make. As a result of making this pedal, I had to go through the process of hardware design from beginning to end. And where this is relevant is, if I said to you, Brandon, sorry I'm picking on you again, can you reason about that circuit?
No.
If I said, is that component working? You can take it out, right, and test it individually. If I showed you how, it's a lot simpler to then do that. If I said, again, sorry I'm picking on you so much, but can you add a ground bus to this? If I explained what those two concepts were, you could probably do this, and bam, we're done, right? Quite simple when you have one component and there's an easy kind of method for testing and changing, right? The pace of change is quick, the cost of change is small. So that's what we're really going to talk about here. And I've been through this whole process with hardware design now, and it's given me some thoughts on, what this means in terms of software design. Productionized hardware is hard, and it's costly in a way that software isn't. So anyway, I got this pedal, designed it, released it. I think I'm on my third iteration of the PCB, and I'm now looking at ways of making it in greater quantities. I'm also interested in tube amps, as the title suggests. I built a bunch of amplifiers. This is this is actually a true kind of tube amplifier on turret board. What's interesting about turret board is you can prototype circuits on turret board, and you can release production circuits on turret board. While I was building it, I started a small electrical fire. So the thing about software is, we say we set our hair on fire when we make a mistake, but we don't literally set our hair on fire. I had this amp in one hand and it was on fire, and I was trying to kick the plug with my foot to get the live current out of it. The danger of change in software is much, much smaller than it is in physical circuits, right? So the peak voltage on the sucker is like 600 volts. Okay, so if you want to test it, there are test points, there are known coupling interfaces, and they're 250 volts a piece, if not more. So if you don't have a dedicated electrician's digital multimeter, your testing tools could literally be blown up by it, right? So how can you test a circuit that you can't even actually reason about with the tools you've got to hand? These are problems we don't really have in software development, not in the same way anyway. Here's an amp I fixed, right? So I brought this one back in a rucksack from San Francisco because I impulsively bought an amp off a guy on Craigslist. I brought it back in a hiking rucksack, carried it through customs, got it home, and funnily enough, during the process of getting it back in the hiking rucksack, it didn't work on the other end. And I had to work out what was wrong with it, because the whole point of a cheap amp, right, is you don't have to take it to an amp tech and spend a couple £100 getting it fixed. So I got it down to the point of the couple of these kind of VAT trolls here, which are doing the channel switching. And I was like, brilliant, this looks like the problem. Change them, wasn't the problem at all. But because you've got that process of informal reasoning where you build a mental model of what's happening in the circuit, what's happening in this complex system, it means that you can backtrack and change direction to work out where the problem really was. And I'm probably giving myself a bit too much credit. I did look up a lot of stuff on forums on the internet as well, but eventually worked out what was there. So I've touched on it. Informal reasoning, right? What is it? So informal reasoning is just applying logical processes in a kind of non-formal logical context. Like, we're not writing an essay on philosophy or logic, but we're trying to model things in our head. So I've touched on the fact that I build pedals. Here is a distortion pedal, a fuzz pedal to be specific. What is a mental model for this if you know what it is, right? Simply, most distortion circuits have an input, they have an amplifier stage, they have a feedback stage, which may or may not have clipping in it, they have a filtering stage, and they have an output stage. So that's how we might model that and model the signal flow within there. For a web stack, right, to make this more relevant to what we do, we're all programmers, we can model that, can't we? We can go, what does a request response cycle look like? Is a request, a controller, a database lookup, typically, some kind of transformation on the output of that, and a response to the client. So this is how, if we had to debug it, we can begin to step through these steps. And feedback, really, is the other thing that we're looking for in order to diagnose what happens in our systems. And it's also what we look for when we develop systems, right? We've got a GIF coming up. Hey, look at that guy. So the point is, right, if we can't actually, if we don't have a rapid and tight feedback loop, we're basically guessing. I'm throwing a skateboard into this little half pipe, and one of 100 variables can mean that it's actually not going to be there when I jump up and expect then to be carried off by it. So what are the things we do to try and make sure the skateboard is under our feet when we jump back on? We're thinking things like, anybody seen the Brett Victor talk, right? The Inventing on Principle one. It's really, really great, but the whole point of that is that he's pulling a bunch of sliders and seeing the changes in the output of his code. Right, and this is something that we see particularly in functional programming, particularly in Clojure, where I now primarily work, where you have REPL-driven development, and you're writing functions and seeing the input and output as you're programming. But this is also the goal of things like guard and auto test, right? The kind of idea that you're going to change stuff in a code file, and then you're going to get some kind of feedback from that to tell you if you've broken something. It's also the goal of compilers, ultimately, is rapid feedback. And more broadly, I suppose, TDD and XP in general is about getting more rapid feedback to you as a programmer as you're building systems, right? And testing is supposed to help with this process rather than having to throw the skateboard in the well and hope for the best. So bringing this back to a practical example, I've had to debug a lot of audio circuits, and it's absolutely mind-bogglingly hard compared to software debugging. And this is really what provoked the whole kind of rumination on this in this talk. So this is an actual breadboard for a circuit, for a production thing that I built, I make, and I sell. When you develop a circuit, you build it on a breadboard. And the great thing about a breadboard is you can debug it at multiple levels. You can debug it at the components. So when I was picking on Brandon earlier, I said, how would you test that capacitor? So again, this guy here is also represented on this circuit. We can see multiple capacitors. I can test them at the component. I can literally take them out of the breadboard, test them with a multimeter, put them back in if they work. If it doesn't work, I can switch in a new one. I can test at the block level. I can test at this tone stack here, or I can test at the amplifier here, or I can put a test signal through the entire thing. The key things about this are that it's basically a set of transformations, right? All audio signals are. So I know that I can just put test signals through individual parts of it and see a repeatable response. More than that as well, the idea of coupling, which I'm going to come to in a second, we talk about coupling capacitors in audio circuits. So we literally know that there are explicit interfaces for where blocks begin and end in these circuits. But this breadboard has two really, really desirable properties, right? Easy change and easy debugging, which I touched on earlier. So the speed and ease of change is incredibly high. But I can't put this in a box and sell it to you. That's ridiculous. Like, that's not how your MacBook isn't just one of these under the hood with 20,000 parts in it, right? You need to actually formalize it into a circuit. So that's where we begin to diverge from software engineering. Because in software engineering, right, we can write a code file, I can push it up onto a server and it can run. That's my shipped product. That's not the case with hardware. Hardware has to be formalized. And so it begins in this process where you begin to split it out. Like, I've got now I/O board now here. I've got a voltage regulation board. And this is beginning to get actually incredibly complicated. And we see this again in monolith versus microservices, that there are a lot of ways in which we try to handle complexity that often get out of hand really, really, really quickly. And I certainly found that while trying to build out multiple audio systems. So what we're trying to do, right, productionize our hardware. And, oh, there we are, okay. So putting a circuit into production has a number of steps. We start with the breadboard that I've already shown. We then formalize it into a schematic, which is just an abstract representation, right? Same thing as a database schema. It's the same root of the word. Then we have a prototype PCB and we have a production PCB, and then we release it. And then maybe we refine it. But that final step, and in fact, these individual steps here could have like a 6-week or more cycle between iterations. If something doesn't work, then I've got to then redraw that. And what's really interesting is this stage before I've been to where I've had a completely valid schematic and I've then got it made, got it manufactured, I've got it back, put the parts on it, soldered it all together to test it works, and it hasn't worked. And so I've made a minor tweak to the actual layout of the circuit, which is just the physical representation in meat space of that circuit. The schematic is still correct, and it has always been correct, but only the representation in the physical world was wrong, right? And then we've had to go through a 6-week cycle of this. And this is just not the case in software. And yet we sometimes forget that we can optimize in a way that we can't in hardware. So, and then there's a bunch of ways you can actually bring this together. So there is this like explicit connection between the abstract representation, the schematic, and the implementation, which can make it very, very difficult to debug. So handling coupling. I've talked about coupling before, but the important real takeaway from this, right, is that analog signal flow in a lot of ways is kind of analogous to the way control flow and the way that data flow work in our programs. And in a lot of ways, it's also analogous to the way that functional programming works. Sorry, I have to mention functional programming because it is a simpler way for thinking about how state moves through our programs. For an audio circuit, if I put the same, well, you see, here's the thing, right? If I put the same signal in the beginning of this amplifier, I would expect to hear the same sound at the end. If it's a different sound, then I know something else is happening, and I can begin to use this informal reasoning model to work out what that might be. A prime example would be if you have a fluorescent light above a circuit as you're working on it, that can actually introduce noise into the circuit. So if you're standing there going, why is this so noisy? Just turn off the light. Granted, you're now there in the dark, which is not particularly helpful when you're working on a high voltage circuit, but the noise will probably go away. So it's that kind of, there's a number of different things will allow you to kind of isolate what the problems you might be having are. And so, yeah, like I said, analog signal flow is sort of, for the most part, analogous to data flow. And it means that we can think about what are the interfaces in our systems, or what are the points where transformations happen a bit more effectively. And this is not really limited just to functional programming, bearing in mind that Ruby, Python, and all these kinds of primarily object-oriented languages have very, very strong capacity for functional type thinking about how programs work. So, I've put a bunch of thoughts here on what these things, what things you can do to kind of minimize those effects and begin to reason about your programs in the small and in the large a bit more effectively. But the two real key ones are to think in terms of transforms and think in terms of data flow. Like, data should be a first-class citizen of your systems and your programs, even in the small. And when you start to think about that in terms of, a guitar signal flowing through an amplifier, it becomes a lot more clear to you. You're like, hang on, I've been thinking about this all wrong for all these years. I want referential transparency and that kind of thing. So what does this boil down to? Hey, maybe breadboard-driven development is what we want, because we can have this in software. We can't have this in hardware, because I can't just ship you a breadboard. I have to make it into a production PCB. But in software, I can ship you effectively a breadboard, and everybody pays you and says you're a great programmer, right? So our production code base is the same as our development code base. There's not a separation like there is in hardware in the same way. And we know what this is, right? This is continuous delivery. And yet, most of the time we don't do it. And there's loads of tools to actually make this even more granular. So right, even if I just deliver you my development code as production code, I'm effectively already one step of the game in terms of hobbyist hardware. But not only that, we have things like continuous delivery that mean you can rapidly increase your pace of delivery in a way that we absolutely can't in that world, because it's so tied to a physical representation of a thing. And then in the small, you can also use things like the REPL to get literally instant feedback in a way that, again, you can only do when you're breadboarding, when you're messing around before you start making schematics and these things, which involve a lot of steps of change. The pace of change is very quick in software. Okay, so finally, some takeaways. So what we're looking for, feedback is more important than testing. So automated tests are basically a way for us to formalize the feedback process. And they're very, very useful as a result. They reduce mental overhead because you don't want to remember that same incantation you had to run to get the result for that thing you were trying to work out whether it worked or not. But they also reify these feedback paths of a particular thing that you remember to test at that time. The next time that a bug crops up, it's the thing that you didn't think you were going to test for, right? Because you didn't think it was a problem. Decoupling is great, it creates interfaces, right? We have these explicit blocks in audio circuits. We have these explicit interfaces between our systems, particularly in the microservice architecture. How do we manage these? Are we going to manage them with contract validations? Are we going to manage them with schemas? There's a lot of drawbacks to all of these approaches. And then being able to hold a system in your head is the most important thing, and this requires systematic simplicity, which is to say it requires systematic simplicity. Sorry, keep tripping over those words. Is when you're going from a simple thing at the level of literally your classes, objects, your functions, depending on what programming paradigm you're operating in, all the way up to your components. It's not easy to do. It's usually impossible because you're dealing with legacy systems and a number of things as well that are just completely beyond your control. But the most important thing is if you're able to apply informal reasoning to the system because you can hold it in your head, then you're much more likely to make better architectural decisions and better decisions about individual pieces of code within even a single namespace or file. And that's it. And does anybody got any questions? Otherwise, I'll wrap up.
How many production units do you have finished?
Different circuits.
Just one circuit which you can print again and again and again?
I think I've got 6 or 7 at the moment. Although one of them vastly outstrips all the others in terms of popularity. I have like 3 years of back orders if I worked every day of the year currently making them by hand. And the other ones, it's like I have a handful of orders here and there. There's one that just outstrips all the others by a country mile. I don't know why.
Why does that one outstrip all the others?
I assume because it's the weirdest. It's like a digital circuit doing quite odd things, and what it's doing is if a really big audio company like Roland or whoever made that circuit, they would go, oh, this is broken. This is doing something really weird and unexpected, but it's doing something kind of unexpected by design because it's seeding random numbers into the audio engine. So I wrote the code for it as well, and it's effectively collecting a sample buffer and then pushing it through a random number generator to manipulate that sample buffer. So it sounds like it's broken, but if you want a pedal that sounds like it's broken, then hey, hey, look, it's a niche apparently. Who knew, right? I made it for myself, loads of other people want it too. So, yeah. All right, thanks guys. Anyway.